Hello, Calc students. This is Mr. Beck. Welcome back to some online calculus notes. Take a little history of where we've been. In 2.1, we talked about the definition of derivative, and we used the limit process in order to do that. And we also talked about the alternate definition of derivative. 2.2, we introduced like shorter notation in terms of power rule. An example of power rule, f of x is 3x to the fourth. The derivative of 3x to the fourth, you bring that exponent out in front and drop the exponent by 1 to get 12x cubed. We learned about the power rule and just different ways to work with that. We learned derivative of sine and cosine. And then we did a little bit of applications of those derivatives. Now, one of the big things about the power rule, is the power rule is done term by term. But is the power rule done factor by factor? So let's take a look at a simple example. If f of x equals x times x is, and this is f prime of x 1 times 1. And hopefully you guys are screaming no, just like I am. So x times x is obviously x squared. F prime of x should be 2x, not 1 times 1. So this is a big red flag, and I'm going to do this. This is a big red flag. Do not take the derivative factor by factor. You're only taking it term by term. So the big question remains, well, how do you take a derivative of a product? Well, we have a product rule, and I really, really wish I could show you the product rules proof. It is in the book. I highly encourage you to take a look at it. It involves some creative addition and subtraction with the limit process, and it works. How does it work? Well, the derivative of a product, so I have f times g, is the derivative of the first times the second plus the first times the derivative of the second. And obviously I'm talking about factors here. So derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. There are lots of different ways that students memorize this. It doesn't matter to me what way that you memorize it. Personally, what goes on in my head is I break this up into differentiable functions, u times v, and I say v du plus u dv. As it goes on in my head, it's the way that I learned it as a student. It's the way that I still think about it as a teacher. So as I'm talking to you guys, I will say this. This will have more meaning as we get to the end of chapter 3. But it'll be the derivative of the first times the second plus the first times the derivative of the second. Now, as awesome as this product rule is, it doesn't really show in the glory what all is going on with the product rule, which is why I have this extended product rule here, where if I have 3 functions multiplied out, then the derivative is the derivative of the first times the other 2, plus the derivative of the second times the other 2, plus the derivative of the third times the other 2. And this process could continue on and on, but what I love about seeing this is it allows us to say, well, every function changes in a certain way. Like here, I have 3 different functions, but how does the combination of all 3 functions multiplied change? Well, each function's change gets distributed to the other 2 functions. So that way, every function's change is represented in the derivative. So with the very first problem that I have here, what I did was I first broke down this first factor. I called that f. The second factor I called g. And so I wrote it out as, well, this is what I'm calling f. This is f prime. This is what I'm calling g. This is g prime. And then anytime I learn a new rule, I tend to write it down over and over again until I have it memorized. So f prime g plus f g prime, or derivative of the first times the second plus the first times the derivative of the second. So derivative of the first times the second plus the first times the derivative of the second. You'll hear me say this many, many times today. Then, like we do anytime we take the derivative, we always factor it. So what can we take out of both of these? I see an x that's a part of both. I see an e to the x that's a part of both. Factor those out and I have this expression. Why do I care? Because most of the time we're not just taking a derivative, we want to apply that derivative. And to apply that derivative, oftentimes we want to know where does our derivative equal 0, which gives us horizontal tangents. So we see x equals 0, e to the x never equals 0, so this factor does not equal 0. X equals -2, that's where we have our horizontal tangents. For part B, as I look at the setup, what I see is I have a product here, subtraction, product here. So what that means is we're going to have to use a product rule on these 2 terms, we're going to have to use a product rule on these 2 terms, and then subtract the result. So derivative of the first times the second plus the first times the derivative of the second. and then I do it all at once. First times the derivative of the first times the second, plus the first times the derivative of the second. Then simplify the result. Don't forget to distribute that negative. I see a lot of students forget that. And then it looks like we can combine the 6x sine x and the x sine x together into 7x sine x. Oftentimes you might see a textbook that'll factor out the cosine from these two terms. I'm okay if you do that. I'm okay if you leave it this way, because in the end, there's nothing common to all three terms. So I would say leave it. But that choice is up to you. Example number 2, given a function, this is where we get to use the extended product rule. We have our 3 functions. Our goal is to find the slope of the graph of f when x equals 1. So if you notice, I have these color-coded. This is a little bit yellow right now. But the derivative of the green times the other 2 functions, plus the derivative of the blue times the other 2 functions, plus the derivative of the red times the other 2 functions. Now, keep in mind, our goal was to find the slope of the graph. I never actually said find the derivative. Yes, we did find the derivative in order to get there, but because I did not say find the derivative, you do not need to simplify this. It just says find the slope of the graph when x equals 1. So we plug in 1, and that's where these highlighted in yellow, when we plug in 1, they get 0. This is a shortcut for you guys to say, okay, what is it you need to do? If you waste time, simplify this and make a bad algebra error, then it's going to affect your answer. Where it's honestly simpler just to plug in 1 to this derivative. So that's an AP strategy for you. Now I did take this further and said, okay, could I find the equation of the tangent line? Well, I know that f of 1 is 0. Once again, if I plug in 0 to the original function, I know that f of 1 is 0. So the equation of the tangent line is y minus 0 equals the slope that we found, 42, times x minus 1. Then we have our quotient rule. Our quotient rule, if you notice, looks pretty similar to the product rule, where the product rule is f prime g plus f g prime. This is f prime g minus f g prime. So we now have a subtraction instead of addition from the product rule. So quotient rule, we have subtraction, and then we divide also by g squared. So big differences, and I teach this order intentionally with the product rule because when it comes to the quotient rule, it's just the same order but subtracted. I do see too many students who like to flip that order, which hurts on the inside, hurts me, hurts them. So moving on. There are some teachers out there who like to refer to this as high and low. So they say low D high minus high D low over low low. If you ever see that on the internet, it's a thing. I'm personally not a fan of it, but that's okay. If the world were just like me, it would be boring. So very first time that I take a look at the quotient rule, what I did was I broke it down into the f function and the g function, meaning the numerator and the denominator. And then, like I told you before, anytime I use a new formula, I like to write it out until I'm very, very comfortable with it. Highly encourage you to do that too. So it would be the derivative of the first, or the numerator, times the denominator, minus the numerator times derivative of the denominator over the denominator squared. And then simplify. I know that this doesn't factor, so I move on. We have numerator, or derivative of the numerator times the denominator. Let me go ahead and color code that for you. You probably understand already. So we have the numerator, derivative of the numerator times the denominator, minus the numerator times the derivative of the denominator over the denominator squared. Then simplify. There's nothing common to both, so we move on. A little bit more complicated function. Derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over our denominator squared. And then I get to this step, and there's not really a whole lot of combination that I can do. So write it out that way. One of the things that you'll notice is, and it comes from this g of x squared, that your denominator will always gain a power every single time that you work through it. And the reason for that is kind of like what the power rule does, that if I have x to the negative first, so if y is x to the negative first, dy dx is negative 1 over x squared, you notice that denominator gains a power. You can see that also, like if y equals x to the negative 7th, dy dx is negative 7 over x to the 8th.
So just kind of a way to check yourself whenever you're working with the quotient rule, your denominator will always gain 1 power every single time. Excuse me. But now that we know the quotient rule, we can take a look at some of the other trig functions, really all the other trig functions. The derivative of tangent, if we turn tangent into sine over cosine, excuse me, we have derivative of the numerator. Once again, let's color code that. We have derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. Now, just so happens that we end up with our Pythagorean triple, cosine squared plus sine squared, which is 1, and then we will write that as secant squared. I'm going to pause this so I can cough one more time. Hold on just 1 second, guys. And now that I've had my drink of water, let's continue. So the derivative of secant, we know that derivative of secant, if we write secant as 1 over cosine, apply the quotient rule, derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. It simplifies, the two negatives cancel. We have sine over cosine squared, which if I break it down this way, what it allows us to do is it allows us to see secant times tangent. That's not a minus, that's times. So if I write out all the 3 trig functions, or the 3 basic trig functions, keep in mind our 3 basic ones are sine, tangent, and secant. We now have all 3 of these derivatives. Some of you might be asking what this du dx is. I'll explain a little bit more as we get into 2.4, which is the chain rule. So officially, these are the chains. So we're not going to be there yet. Derivative of sine is cosine. Derivative of tangent is secant squared. Derivative of secant and secant tangent. Personally, when I was a student, I memorized this, and I totally regret that because I had you derive all of these for the reason, just because the more you derive them, the more you know. Now, our 3 basic trig ones, like derivative sine has a cofunction, tangent has a cofunction, secant has a cofunction as well. There's a relationship between all of our cofunction derivatives. If you notice that we have sine and cosine here, those are cofunctions of each other. Secant squared and cosecant squared are cofunctions. Secant and tangent, cosecant and cotangent, these are also cofunctions. So what ends up happening is if you know these 3 derivatives, you can figure out these 3 derivatives very, very quickly just by taking the opposite. Notice how all the cofunctions derivatives are opposite or negatives, but the opposite of the cofunction of what it came from. Simple, right? So y equals 2 sine x cosine x. Our goal is to find the derivative. So 2 cosine times cosine. So derivative of the first times second plus the first times derivative of the second. Simplifies down here. Now, a lot of people are saying, wait a second, I mean, we already did problems like this, but one of the things I wanted to show you is if I see cosine squared minus sine squared, then personally, I think that there is a double angle formula, cosine 2x. I know a lot of students are like, ooh, yeah, I sort of remember that. That's fair. This is our opportunity to bring some of that knowledge back to mind. So then 2 cosine of 2x, if we can combine it down here, we probably could combine it up here. And oh, wait, we can. We know that this expression is sine of 2x. So there is a relationship between this and then this derivative, which is 2 cosine of 2x. Foreshadowing. Ooh. All right, b. B is sine over cosecant. So a sine over cosecant, we have derivative of the numerator times the denominator minus the numerator times derivative of the denominator. And I went through all of this. And as I go through all of this, what ends up happening is I have 2 sine of x cosine of x. Excuse me one more time. So 2 sine of x cosine of x, which I probably could have gotten that a lot faster by just turning this sine over cosine into sine times cosine. So with that said, example 6, our goal is to find f double prime of x, which means we have to first find our first derivative. Derivative of tangent is secant squared, we know that one. And then if I break it up into secant times secant, then I can use the product rule. Derivative of the first times the second plus the first times the derivative of the second. And now these can be combined into 2 secant squared tangent of x. Then our second problem, if I want to find the derivative of cosecant, I went through the proof of on here just because I wanted to have a good time with it. So f of x is 1 over sine, f prime of x is
ends up being negative cosecant cotangent. Defined f double prime, derivative of the first times the second plus the first times the derivative of the second. Notice how I said plus the first, that first term is, or first factor, excuse me, is a negative. Now all that simplifies into cosecant times cotangent squared plus cosecant squared. So pretty exciting. I know you're thrilled. I am definitely thrilled also. One of the things that I did want to mention is when you have derivatives, we say dy dx, we call that f prime of x. If I want f double prime, then I will write it as d squared y over dx squared. F triple prime, d cubed y over dx cubed. And then eventually, if I get the nth derivative, or anything beyond that, we usually write in parentheses in the Newtonian notation. Now, when it comes to the Leibniz notation, we say d to the nth power of y over dx to the n. Now, what's really happening here is we are saying how many derivatives are we taking with respect to x of the function y. So a lot of students are like, why is that exponent here instead of out on the outside? It has to do with how many derivatives we're taking. So with that in mind, last but not least, we could take a numerical approach to this if we have a table of values and we have a function, which the AP loves to do. So that way it's students don't, they're not just learning the algebra, they're learning the ideas behind it as well. So once again, derivative of the first times the second plus the first times derivative of the second. You know I'm saying this just so that it's stuck in your head over and over and over again. We go to the table and we say, all right, f prime of 3, which is what we're trying to find, h prime of 3. So f prime of 3 is -5. G of 3 is just 6. And then plus f of 3, which is -3, and g prime of 3, which is 1. And then simplify our result of -33. And all these are the same. So we just apply the appropriate rule. The only thing that I would like to point out is this one right here. Notice how I wrote this as G over F. One of the reasons why I did it this way is because the AP likes to do it as well, and it forces you to make sure you're not just memorizing the formula. The derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared, and then put it in and simplify. So H is a big setup where eventually, next time, we're going to talk about 2.4, and 2.4, which is the chain rule. But when it comes to 2.4, I just want to show that if we take the product rule, we end up with 2f prime f and 2g prime g, which then when we go to the table, we can simplify it. I hope you guys enjoyed this and have an amazing day. We'll see you next time when we talk about the chain rule.